turning my microphone on will probably help with that. Hey. Okay. So, here in from the homework. Yeah, we could do one like that. Let me pull that up. From homework 6. Huh. So I actually had a problem like that that included finding critical points and then going forward. So we can start with that example, and we'll start with finding the critical points. So just that was the one that was right? And it said find crit points. So we'll start with that example that looks a lot like that and will involve finding all of the different things that are today, which includes crit points but is not limited to. Okay, but first let's get an idea of what we're talking about with this section down. So as I wrote here when I couldn't figure out what my mic was doing, by shape of a graph, what they actually mean is concavity. Right? So if we have a picture of a function that looks like this, then what we did last section tells us that this is a critical point, this is a critical point, and this is a critical point. And this is increasing, this is decreasing, increasing, and decreasing. Right? So for this section, we're going to be doing the same sort of thing. So I'm going to try to draw the exact same picture. That's close enough. But here, we're talking about concavity, not increasing and decreasing. Right, so this is concave down. These are both concave up. And these turning points, things that take place at points, are inflection points. So the definition of concave up involves the derivative increasing, and we learned last time that a function increasing means that its derivative is positive. And similarly for concave down, since that means the derivative is decreasing, and we know a function is decreasing when its derivative is negative, the derivative of the derivative is the second derivative, so we're going to be using this guy to do it. And inflection points, like we mentioned up there in the graphs, are like max and mins, but they're for the second derivative instead of the first derivative. So 1, the first derivative of the c has to be 0, or it needs to not exist, right? And the second derivative needs to change signs, right? So if we draw this out and we have c, it either needs to be positive on one side and negative on the other, or negative on one side and positive on the other. Right? Now, if we were doing this for the first derivative, one of those would tell us that it's a maximum, and the other one would tell us that it's a minimum. But for inflection points, we don't distinguish between those guys. Regardless of what direction it goes, it's still just an inflection point. And lastly, what we learned from this book is the second derivative test. For extrema. So remember, that was our fancy word for max and min. Right? So if C is a critical point, so first you still have to find critical points, even if you're using the second derivative test. Then if we plug that critical point, not the inflection point, the critical point, into the second derivative, and it's positive, we get a minimum. If the second derivative is negative, we get a maximum. And if the second derivative is equal to 0, who knows? It tells us nothing. We don't know that it's neither. We don't know if it's a min or a max. It could be anything in the world. So hopefully we don't get too many of those. So, to start us off on a problem, we'll do the one that's like number 9 from the homework, but we're going to do more with it, right? So we'll do what the homework requires first, and then we'll find the rest of the stuff about it. Right, so we're going to find the critical points, the inflection points, the intervals of increasing, decreasing, concave up, and concave down. Then we're going to classify all critical points 2 ways. Right? So classifying, oh yeah, sure. Classifying critical points means deciding whether they are maximums, minimums, or neither. right? Those are the three options for critical points. And that's what we mean by classify, is to figure out which of those are. And the two ways we have, right, just as a reminder, are the first derivative test and now in this section we have the second derivative test. And to do this, we need a function. And it's not exactly like the homework problem, but let's go ahead and make it really similar to the homework problem. It means I'll do a little bit more off the cuff, but we did want to do one like the homework problem. Are we good? Or do we want to pause here for a second? Okay. So, we said we wanted to find the crit points first because that's what the homework problem was. So how do we find crit points? So this one, remember, is thinking back 2 whole sections ago. What were we talking about then? How do we find critical points? Yep. So the crit points we find by taking the first derivative, right? So we need y prime. So what do we get for the first derivative of this function here? What rule do we need to use there? So what type of piece of the original function is that? That's not quite a rule that we have. Right, that is part of the function. But what type of part of the function is that? That might have to do with our derivative rules. Right, the product rule. Right, that e to the negative x is a factor of the original function. So since we have two factors, we're going to need to use the product rule. Right? So the product rule says we want the derivative of the first times the second. So what's the derivative of x minus 2? What do we got for the derivative of this piece right here? That polynomial x minus 2. One. Now what's the derivative of e to the negative x? Right? Because the other piece of the product rule is to take the derivative of the second and multiply it by the first. So now we need to look at this factor. Yeah. Alright, so that uses the generalized exponential rule, which where to take the derivative of that, you just write the same thing over again, but multiply it by the derivative of what's in the power. So this is e to the negative x minus x minus 2 times e to the negative x, which is 1 minus x plus 2 times e to the negative x. So that is 3 minus x times e to the negative x. Right. So, Kaylee mentioned before that we're going to be setting it equal to 0. Right, that is in fact the place where we're going to get critical points here. Where else might we possibly get critical points? Not in this situation, but in others. 0.7? Yeah, it does not exist. But with a polynomial and an exponential rule, neither of those have places where they don't exist. Right? So that's something we need to keep in mind, but not worry about for this problem. So, how do we solve this equation? So, really we want to, whenever we have something in factored form, we can set each factor equal to 0. Right? This one, the 3 minus x equals 0, is the only one that really matters. Right? Because an e to the whatever is never going to be equal to 0. So there's no solutions over here. But over here, we get x equals 3. So, for critical points, we have x equals 3. So, we have checked off that piece. So, let's go ahead and stick with the stuff that we can solve using the first derivative. So, of the rest of the stuff we need to do, inflection points, increasing, decreasing, concavity, classifying, what can we do using the first derivative that we've already found? So what of all the stuff we have written up there did we talk about last time? Right? Because last section was all about the first derivative stuff. This new section was all about the second derivative stuff. So which stuff did we talk about last time? Well, while we're maybe trying to think about anything else we talked about 2 days ago, we can go ahead and start with the thing on the board that's written down as first derivative test. That's probably going to use the first derivative. So how do we use the first derivative test to classify crit points? What rule did we talk about last time that helped us figure out whether a critical point was going to be a maximum, a minimum, or neither? What sort of thing did we do? So one of the things we did was we drew a number line, and we put all of our crit points on it. And then we did a lot of playing the game of what's your favorite number. So what's your favorite number that is less than 3? With the only thing being you're trying to make it as easy as possible on yourself to plug in. Yeah, that works out for us. So we take our favorite point from that interval, so 2, and we plug it into the first derivative. That's why it's the first derivative test. So we get 3 minus 2 times e to the negative 2. Is e to the negative 2 positive or negative? going to be positive, right? Because E is a positive number. And it doesn't matter... Oh, we weren't there yet. Quite there yet, Kaylee. But we can plug in 4 next. But E is a positive number, so it doesn't matter what power you raise it to, you're going to get another positive number. Right? So the next thing would be picking our favorite number bigger than 3. And 4 is a perfectly good option for that. So is negative e to the negative 4 going to be positive or negative? Are we sure? How do we get positive? Right, because remember, this negative 4 here is not being multiplied by negative e. It's in the power. Right? So like I just got done saying over there, e is a positive number. So if you raise e to anything, you get another positive number. And if you put a negative sign in front of a positive number, it becomes negative. Right? So just as a note, this is different from negative e to the negative 4. Right? If you want to raise the negative to the negative 4 power, then you have to put those parentheses around it. Anytime you don't see parentheses around it, that power is just affecting that first number that is right on top of. Right? No other part of it. That can be tricky, but that's why we have the parentheses going around, is so that we can be very clear about what's being raised. Right? Because if it was negative e to the negative 4, you're absolutely right, it would be positive. Right? But since that negative is not actually being raised to the negative 4, it sticks around and turns the rest of it negative after we're all done. Right? So, what we have here is a change, right? As it goes through this 3, which is the critical point, it's positive on one side and negative on the other. So this tells us that 3 is a local max. Right? And that's what the first derivative test tells us. So, we have now classified the critical point one way. So what else on this list can we figure out using the first derivative? Can we use decimals? I'm not quite certain what you mean in terms of... Oh yeah, absolutely. To plug in, like if you want to find your favorite number less than 3, yeah, you could absolutely have plugged in 2.5. But remember, the point of picking a number, right, is to find as easy, something to plug in that is as easy as possible, as easy to evaluate. which sometimes fractions are necessary, right? If we had a critical point at 2 and 3, we would have to use a fraction like 2.5. Often, if you don't have to, it's going to be easier to plug in integers. But yeah, when I ask for what's your favorite number in this interval, as long as it's within that interval, you are fair game to plug in whatever you want. So, what else from this list of things that we need to find did we talk about last time that involves the first derivative? Increasing and decreasing are something that we have learned as a quality that we can figure out from the derivative. So what about the derivative tells us about increasing and decreasing? Because, handily enough, the reason why we have one problem that has like 6 pieces is because usually the work that solves one of those pieces is going to get us another. So we actually have all the information we need already on the board here. We just need to write it down as our answer. So what tells us that a function is increasing? Right? The derivative being positive. So a function is increasing whenever its derivative is positive. Right? So we've actually already figured that out to use the first derivative test. So we can pull this down and figure out that negative infinity up to 3 or x being less than 3. Right? Those are 2 ways to write down the same answer, is where it's increasing. Right? And to go along with that, whenever the derivative is decreasing, or negative, the function is decreasing. Right? So the minute you've done the work to classify using the first derivative test, you already know increasing and decreasing. Right? The stuff from this section is even better. We have one thing to do that tells us all the information we want. Yeah, it's pretty much the same. It's not actually all that much more. So, now we have increasing and decreasing. So these are all the things we can do with the first derivative. So inflection points, concavity, and the second derivative test all require the second derivative. So I'm just going to do it as one big piece here. So let me get to a point where we see, there we go, we can see what y prime is. All right, so what's the second derivative of y? What rule do we need to use to take that derivative? How are we going to take the derivative of this function? What rule do we need? What are we doing there in that function? Well, it looks like that's another product. So we probably want to use the product rule. All right, so the first factor is 3 minus x. What's the derivative of 3 minus x? There we go. Well, 3 minus x is another one of our polynomials, so we just got to use the power rule a couple times. And for the other term, we're taking the derivative of e to the negative x again. We already figured out what that derivative was, so we've got this guy here. So we have our second derivative. What needs to be true, or what do we need to do to find inflection points? So if we recall from way back at the beginning of class, finding inflection points are like finding maxes and mins, but for the second derivative, right? And to find the max and min, what we did was we set the first derivative equal to 0 or not existing. And then we did our number line thing to figure out whether those critical points were maxes or mins. So to do the same thing for the second derivative, we need to figure out where the second derivative is equal to 0. Or not existing. So is the second derivative ever going to not exist? So the second derivative is never going to not exist, because polynomials always exist everywhere, and exponentials also always exist everywhere. So if all we've got is a product of those two guys, it's always going to exist. So we don't have any not existing. And for being equal to 0, we're going to do the exact same thing that we did above. We're going to take the two factors and set equal to 0. We're going to get no solution over here, because e to the anything never equals 0. And we're going to get x equals 4 over here. Right, so there's no real correspondence to critical point, or at least there's no name for it, right? But that would be the sort of, this x equals 4 would be the equivalent of a critical point just for the second derivative. We just don't have a name for it, right? Because in order for it to be an inflection point, we have to know already that it switches from positive to negative or from negative to positive. Right? So what's our favorite number less than 4? 3. Sounds good to me. So we already talked about how e to the whatever is always going to be positive. So if we put a negative sign out front, that means we're going to get negative over here. And what's our favorite number bigger than 4? 6. Sounds good to me. So we plug that in and we get 2 times e to the negative 6. E to the negative 6 is going to continue remaining positive forever. If we take a positive number and we multiply it by a positive number, we get another positive number. So that means 4 is an inflection point. Right, because it goes from negative to positive. So having done that, having made that chart there, we know where it's concave up and concave down already. So where is it going to be concave up and where is it going to be concave down? Zoom it past the point of usefulness, but maybe we can still read that up there. Maybe I can at least remind you where in your notes it might be. So what do we have about when a function is going to be concave up? Yeah, concave up is when the second derivative is positive. So if we look down here, that's going to be from 4 to infinity, or in other words, x is greater than 4. And concave down is going to be the opposite. It's going to be when the second derivative is negative. So we've got the rest of it there. So the last thing, let's see, going all the way back up here, we've gotten inflection points, we've gotten concave up and concave down. Now, the last thing we need to do is classify the critical point that we have using the second derivative test. So what do we need to do in order to classify a critical point using the second derivative test? And that's actually not going to help us out much. I'll go ahead and zoom into our second derivative here. Actually, we do need to know what our critical point is. Which, there we go, x equals 3. So the second derivative test, to tell what to classify a critical point, says to plug that critical point into the second derivative. Now, we were clever enough to have already done this, so that's pretty cool. Right. And the rules for second derivative test have to do with whether it's positive, negative, or 0. Right? Hopefully not 0, because if it's 0, that causes us problems. But we've also already said that this is less than 0. Right? So according to the second derivative test, if when you plug in the critical point to the second derivative, you get a negative number, this tells us that we have a local max. Which is good, because we already figured out it was a local max. And if we somehow determined that this was a local min, we'd need to go back and check our work somewhere. Either our second derivative, or when we plugged it in, or maybe the work we did to find the local maximum, something would be wrong. Right? But this is classifying it using the second derivative test. So, do we have any questions about anything here? There we go. Any of those steps we want to talk about anymore? Okay. So if there are any questions, we can always go back. Don't worry about it. But I'd like to go through one more problem. And we're gonna go through it a little bit quicker. I'm not gonna stop and ask for input quite as much, because that apparently seems to be not our mindset today. And I want to make sure we get through one more in the 12 or so minutes that we have, just so that y'all can have seen some practice. So we got ourselves a new function, but we want to find all those same things that we were looking at before. The first thing we need to do is find the first derivative. Right, so this is going to be a couple uses of, the logarithm derivative and the generalized one. Yeah. Like, that far? How far do you want me to go? Excellent. So, that gets us just our rule for the derivative of natural log. And then for the natural log of a more complicated function. So there's two ways again to find critical points. One of them is the function not existing, right? And since with this function we're dealing with fractions, we're suddenly in a position again where the derivative might not exist, right? If all we're dealing with is polynomials and exponentials, the function is always going to exist. But here where we have fractions, we have that the derivative doesn't exist, but we note that these are not in here, right? So when we specified from 0 to 3, with the parentheses like that, that means that those aren't actually in our domain. So we're going to wind up throwing those out as critical points. Right? So hopefully we'll get something from here. We might not. We might not have any critical points, which is perfectly fine. Right? So we get... So y'all might remember from a bit ago, like not even in this class a bit ago, something called cross multiplying. If you have two fractions being the same, then you can cross multiply with them. Here in algebra or pre-calculus or calculus, anything where you got variables, you have to be careful that the variables, that the denominators are not equal to 0, but that's why I did that does not exist first here. Right? So we're not allowed to cross multiply if x is equal to 0 or 3, but we've already covered that case, so we can go ahead and cross multiply. Right. And we get x equals 3/2. Right? So our critical points, we really just have one again. Right? Because again, there are some places where f prime doesn't exist, but they are not in this domain. Right? 0 and 3 are not in that open interval. So they're not actually critical points because they're not part of the domain of the function. So we have to set ourselves up again. Right? And one thing we might notice is that we actually have secret caps here of 0 and 3, right? Because again, those are our domains, so when we're picking our favorite number, we have to choose something in between 0 and 3/2, right? Because again, this part of the problem here says that we're not allowed to look at x's that aren't in between 0 and 3. So I choose 1. Right, so that's 1 minus 1/2. That's positive. And now I need to choose a point between 1.5 and 3. I choose 2. So here we get 1/2 minus 1. That's going to be negative. All right. So we can see that the function is going to be increasing from 0 to 3/2 and decreasing from 3/2 to 3. Right, again, we have got that 0 and 3 instead of the negative infinity and infinity because our whole problem has to live inside that world up there. Right. And the first derivative test says that x equals 3/2. Well, we're increasing and then we're decreasing, so it must be a local max. Right. So, that's all the stuff that we can get out of the first derivative, and then we have to go to the second derivative to get the rest of the stuff the problem asks for. So the first term is pretty easy to take the derivative of, not a problem. Just using the power rule. The second one kind of requires the quotient rule. We could do it a little bit simpler using the generalized power rule. Right, so I'm going to write this as right, so instead of writing it as a fraction, we can write it as a chain rule type problem. And you can also use the quotient rule if you want. I just really don't like the quotient rule myself, unless I have to use it. Sometimes it's easier than others. Right, if there wasn't a 1 up top here, if this had been something with an x in it, then it's going to be easier to use the quotient rule. But as far as we got there, we're good. Okay. So now we want to find inflection points. Right, so it turns out that the function, again, doesn't exist on 0 to 3. Right? These are not on the interval that our domain is, so we're going to wind up not needing to care about those. But it's good practice to check for them. Right, so again, we want to solve for this guy. Oops. And again, it's going to come down to cross multiplying. Right? The only problem with cross multiplying is when the derivative equals 0, and we've already taken care of that by doing the does not exist first. So we get so I multiplied out that 3 minus x squared. And oh hey, look at that. We got x equals 3/2 again. Right? So if we plug in to our number line, again, we secretly have these caps of 0 and 3. I'm going to plug the exact same thing in again, because those are still my favorite numbers. So now we have -1 plus 1/4. That's going to be negative. Here we have -1/4 plus 1, and that's going to be positive. So we do have this switcheroo here. So we have that this guy is an inflection point. We have concave down from 0 to 3/2. We have concave up from 3/2 to 3. And one of the nice things about working it out this way, or when it works out this way, is the fact that we got 3/2 here and 3/2 here. Well, really, that first one tells us that f double prime of 3/2 is equal to 0. We don't have to work that out again. That's what this whole piece of the problem was figuring out. Right? So the second derivative test is inconclusive. I'm just going to scooch this over here a little bit. Right, so as far as the second derivative test is concerned, we have no idea whether 3/2 is a max or a min. Thankfully, the first derivative test was a little bit more helpful. But in this case, the second derivative test doesn't tell us anything. Right? Remember that equals 0 means it might be a maximum, it might be a minimum, it might be neither. Nobody knows. Okay. So we are a chunk over time, but I wanted to get through one and make sure we saw what happened when we got that sort of inconclusivity. There'll be a new homework opening up as usual tomorrow when the quiz ends. That will be our last homework, because next week is the last week of classes. There'll be an announcement going out sometime today or tomorrow about how we're going to do the final exam. So keep an eye out for that. Does anybody have any quick questions they want to shoot off before we run away for other things that are happening. Alrighty, I'll see folks on Friday where we'll talk about L'Hôpital's rule.